evening, friends. Myself, Mahesh. I welcome you all on behalf of ACE Engineering Academy. In this particular session, I am taking a small concept related to the shear force and bending moment analysis in case of beams. What exactly the shear force, what exactly the bending moment, how it is developed in a loaded beam, how we can find out the shear force as well as the bending moment at one particular section, and what is the relation between applied loading conditions as well as developed shear force and developed bending moment. This part I am going to be covered, and some 2-3 numericals we try to solve by applying that relations. Now let us begin the session. So what exactly the beam? As we know, beam, it is a structural member subjected to the lateral loads as well as bending couples. As we know, it is a structural member which is subjected to the lateral loads or transverse loads as well as bending couples. So when we are applying the loads on the beam, to maintain the equilibrium condition, some kind of internal forces are generated in the beam cross section. That internal resistive forces are having two components. One, shear force, second one, bending moment. For example, if it is a beam, now when we are applying the load on the beam, to maintain the equilibrium condition, some kind of internal resistive forces are going to be generated. One force, if you are observing, it is acting parallel to the cross section, what we call it as a shear force. And the second one, it is giving the movement effect, that is nothing but bending moment. In this particular session, we will try to observe what exactly the shear force, what exactly the bending moment, how you can find out the shear force as well as the bending moment at one particular section. First, we are taking that part into the consideration. Now, how you can define the shear force? Shear force, it is nothing but equal and opposite force acting along the transverse axis of the member. Now, you can take this one. If I take a beam something like this, this is the cross section of the beam, this is the longitudinal axis, and this is vertical transfer axis, this is a horizontal transfer axis. Shear force, it is nothing but it is the equal and opposite force at any section that is acting parallel to your transfer axis. When I am speaking this force with respect to longitudinal axis, it is nothing but equal and opposite force which is perpendicular to the longitudinal axis of the member. We call that as a shear force. Now, how we can find out the shear force at a particular section of a loaded beam? What is the principle we are going to be used to find out the shear force at any section of the loaded beam? Now, let's see. Suppose if it is a beam, this is a beam, just imagine. Now, I am applying some forces on this beam at various cross section. Here I am using a point load, here I am using partial UDL, and here I am using a triangular load, something like this. And when I am applying the loads, immediately these supports are giving the reactions against these applied loads. And hinge, it is giving the 2 reactions, but roller, it is giving the 1 reaction, as we know that. But in the analysis of shear force and bending moment, we are not involving this horizontal reaction. Now, when I want to find out the shear force for this loaded beam at any one particular section, what is the criteria we are going to be using is, let us take the section at here. If I consider the section at here, this is the left part for the section and this is the right part for the section. Now, how you are defining the shear force at any section is, it is nothing but algebraic sum of the transverse forces including the support reactions, either left hand side of the section or you can consider right hand side of the section. So algebraic sum of all the transverse forces including support reactions, either you can consider left hand side of the section or you can consider right hand side of the section, that is giving the shear force at one particular section. See here, suppose the resultant of all these transverse forces are, just imagine if it is acting something like this in downward direction for my left hand side of the section, then this force I may consider as a shear force acting at this particular section. If my shear force is acting vertically downward left of my section, then right of my section, it must be acting in a upward direction. Equal and opposite force that we are observing along the transfer axis, we call that as a shear force. Got my point? Yes, another possibility we are having, suppose if the shear force left hand side of my section, if it is acting vertically downward direction, here we are showing, suppose if it is acting vertically upward direction, when I am adding all these forces, my force, suppose if it is acting vertically upward direction, then right hand side we are observing a vertically downward force. Both are always under balanced condition. So here we are observing two possibilities for the shear force at any section. Being we are having two possibilities, we need to assign the sign convention for the shear force analysis. What is the sign convention we are using? Let us take this one. For analyzing the shear force at any section, what is the sign convention we are using is, now let me take, this is the beam I am considering, this is the section I am taking. For my section, this part is right hand side and this part is left hand side. Suppose when we are observing the force in upward direction, right hand side, first I am considering right hand side upward force we are consider as a negative force. Suppose if I am having the force, when I am considering the left hand side forces, left hand side if you are observing your force is acting in downward direction, you can take it as a negative shear. Here we are observing this is negative shear. That means left hand side downward force I may consider as a negative, right hand side upward force I may consider as positive when we are doing the shear force analysis. Now come down to this area. Now this is the section we are having for the loaded beam. Now this is the right hand side for my section and this is left hand side for my section. Now what is the sign convention we are having is, if you are identifying your force is acting vertically downward right hand side, then this force I may consider as positive, my dear friend. Suppose left hand side, if you are identifying the upward force, left hand side upward force, I may take it as a positive loop. So regarding positive sign, when we are having a positive shear, in case of left hand side, if your force is acting upward direction, then it is considered as positive shear. In right hand side, if your force is acting downward direction, then we can consider it is a positive shear. Now this is negative, my dear friend. This is negative. This is a negative sign we are having. Just I am showing it here. So this is the sign convention we are using when we are doing the analysis for the shear force. See, whenever the beam is loaded, in addition to the shear force, another internal force is also going to be developed. That force we may call it as a bending force or bending moment. So how you are defining the bending moment? It is nothing but equal and opposite moment about a transverse axis of the member. For example, if you take a loaded beam, suppose I have a beam something like this, I am applying the load, that load it is giving the generation of internal resistive forces. Suppose this is my section I am taking. For my section, if my bending moment, this side if it is acting in an anti-clockwise direction, left hand side, then obviously right hand side of my section, we are observing a clockwise bending couple. Then only the beam it is at a rest position. Similarly, another possibility if you are having Now, for my section, if right hand side, if my resultant bending moment, if it is acting in anti-clockwise rotation, yes, here left hand side of my section, the resultant bending moment we are having in a clockwise rotation. Then only the beam it is under a rest position or it is under a equilibrium condition. Now, if you are observing for the section either right hand side or left hand side, if you are considering two possibilities we are having again for the bending moment. So when we are finding the bending moment at one particular section, we need to assign the sign convention. Now, first of all, before taking the sign convention, how you are finding the bending moment at a particular section. So what is the method we are using to find out the bending moment at one particular section? Now, for example, let me take this one. This is a loaded beam I am going to be consider. I am applying the loads. These are the support reactions I am going to be take. Here I am using one point load. Here I am using one concentrated moment. Here I am using some partial UDL, something like this. Somewhere on this loaded beam, I want to find out what is the bending moment acting at this particular section. Now, when I am taking the section, I have two possibilities for me. This is the left hand side of my section and this is the right hand side of my section. Now, how you are finding the bending moment at this particular section? It is nothing but an algebraic sum of the moments of all the forces, either left hand side of my section or right hand side of my section. It is giving the bending moment acting at this particular given section. When we are taking the moment of all the forces, we need to include the support reactions also in the calculation of a bending moment. Now, simply I can say bending moment at any section, it is nothing but an algebraic sum of moments of all the forces, either left hand side or right hand side of my section. Then what is the sign convention we are having for the bending moment calculation? Let's see. Suppose because of application of forces, if the beam is going to be bent something like this. Now, here if you are observing, this is my section I am taking. For my section, this is right hand side part. And this is left hand side part. Now look at here, right hand side when I am considering, I am using anti-clockwise couple at this end. Here I am using clockwise couple left hand side. When I am applying the clockwise couple left hand side, now look at here, your observation, if you observe this layer, top layer is under compression, bottom layer it is under elongated condition, which gives the tension for this one. Similarly, when I am considering right hand side part for my section, when we are giving the anti-clockwise rotation, top layers are under compression, bottom layers we are observing under tension. This type of bending moment I may consider as a positive bending moment. In positive bending moment, top layers are under compression, bottom layers are under tension. This is also known by the name sagging bending moment. Sagging bending moment I may consider as positive. And what about the negative bending moment? Now look at here. So if the beam is bending something like this, now somewhere I am considering the section. This is right hand side for my section and this is left hand side for my section. On left hand side we are giving the anti-clockwise rotation couple. On right hand side we are giving the clockwise rotation couple. So when I am considering the left hand side part, left side part when I am considering, now look at here, when I am using the anti-clockwise couple, now you can observe the top layer it is under tension and the bottom layer it is under compression. Similarly, when you are observing the right hand side part, so if you give clockwise rotation of couple, top layers we are observing under tension and the bottom layers we are observing under compression. This type of bending I may consider as a negative bending moment. Some people call it as a hogging bending moment. So when we are having the positive, when we are having the negative, if I take, just I am writing this one. So first let you consider the left side, then you can consider the right side. First, let us take this one left side. When we are having the sagging moment, clockwise rotation, it is giving the positive bending moment, left hand side. Anti-clockwise rotation, it is giving the negative bending moment in terms of left side consideration. And when I am using the right hand side part, when we are having the positive bending moment, look at here, anti-clockwise rotation, it is giving the sagging effect for the beam, right hand side. And clockwise rotation, it is giving the negative bending effect. This is the sign convention we are using for bending moment, and previously we were observing the sign convention for the shear force. Now, shear force and bending moment are nothing but they are internal resistive forces developed because of application of loads on the beam. Very good. Then what is the relation between the given loading conditions as well as a developed shear force as well as a developed bending moment? Now let us see that. Now my interest is observing the relationship between applied loading conditions as well as the developed internal shear force as well as internal bending moment. Let us see that. I am taking a simple beam, my dear friends. I am taking a simple beam. On this beam, I am applying a continuously distributed load. The load, it may be uniformly distributed load, or the load, it may be uniformly varying a load, or the load, it may be sinusoidal load, whatever it may be. It is a continuously distributed load. For this continuous distributed load, I try to observe the relationship between the rate of loading conditions as well as shear force and bending moment. So when we are having the distributed loads, we know that they are always represented with the intensity of loading condition. Load intensity is nothing but a load per unit length. How much load is acting per unit length of the member. So generally we are representing with the omega, so omega kilonewton per meter. To observe the relation between these three parameters, let us consider any small differential element on the loaded beam. That a differential element I am taking somewhere at here. This element I am selecting at a distance of x units from left support. So the length of this element, it is a dx. Now I try to observe the forces acting left hand side of this section, this particular element, and right hand side of this particular element, as well as the moments which are acting left hand side of this element and right hand side of this element. As we know, this element, it is under equilibrium condition. To get the relationship between these three parameters, we are applying the equations of equilibrium. Let us see that. Now, this is the element I am taking separately. So this is the moment and this is the force. Just imagine that is acting left hand side of my element and right hand side of my element. This is a small elemental strip. The uniformly distributed load, just being element is very small element. Yes, loading distribution, it is almost uniform over this element. Yes, let us consider it is a UDL load, uniformly distributed load. Now when I am converting that uniformly distributed load into equivalent load, when we are doing the analysis of the beam under distributed loads, first of all, we need to take the equivalent load for the distributed load. That equivalent load we are using for the analysis purpose. Now fine, this is omega into dx. It is giving the equivalent load. Where it is acting? It is exactly acting a centroid of this particular differential strip. Now first, let us try to apply the force equilibrium condition and observe the relations. Summation of forces along y direction equal to 0. What is the sign convention we are taking at here is upward force, I may take it as positive. This is the sign convention we are using. Now look at here, when we are taking the forces, we should not consider the moment. Now here one force it is acting, F, that is acting in upward direction. Let us take this is positive sign. And as I move on from here to here we are observing one downward force with a magnitude of omega dx. Being it is a downward force, I am using it is minus sign, omega dx. And as I move on from here to here we are observing one more downward force, that is F plus some change we are observing in the shear force. being it is a downward direction, I can use minus sign as per our sign convention, then it is F plus dF. All these forces together, it should be equal to 0 because beam, it is under equilibrium condition. So when it is at rest position, it take care about the rule of equilibrium. Now simplify this one. If you simplify this one, here F minus omega dx minus F minus dF, it should be equal to 0. Now strike off these two terms, then minus omega dx, it should be equal to df, my dear friends, df. Just I am rewriting this one. If I rewrite this relation, df divided by dx, it should be equal to minus omega. Here the sign minus, it is related to loading, it is in downward direction. As per our sign convention, your load, it is in downward direction. So one relation we are having between shear force and a rate of loading condition. What is that? Now look at here. If I observe this part, let us take this part. If you take this numerator part, it is nothing but change in shear force between any two sections. The change in shear force between any two sections, if I represent per unit length, this is nothing but rate of change of shear force. This parameter we may call it as rate of change of shear force. Rate of change of shear force, it should be equal to mathematically rate of loading acting at that particular section. And when we are plotting the shear force diagrams, as we know, so we are taking the shear force values in y direction along y-axis, and the length of the beam we are taking along x directions. Is it right or not? Exactly. So this df divided by dx, based on this observation, we also know that df divided by dx, this term, it is also known as slope of SFD at one particular point. Slope of SFD shear force diagram at a particular point, it should give the information about the rate of loading acting at that particular point or at that particular section. So by using the force equilibrium condition, we are observing the relation between the shear force as well as rate of loading condition. Now let us use another equilibrium condition. Now this time I am applying the movement equilibrium condition. Summation of movements about O I am taking, it should be equal to 0. Here clockwise rotation, I am taking it as a positive sign. Now let me take this one. Here we are observing one clockwise movement. Just you can take this is positive value. M, why it is positive? Here the rotation, it is taking clockwise. Now here one more force is acting, that is at a distance of dx. This is the distance we are observing between point O and F. Now how it is acting, my dear friends? It is also acting clockwise rotation plus F at a distance of dx. As I move on, here we are observing one downward force, and the distance between point O and this downward force is dx divided by 2. Now being it is giving the anti-clockwise rotation, so use minus sign. Now load is omega dx, distance of this load is dx divided by 2. Why it is minus? It is giving anti-clockwise rotation. Now this force does not create any movement about this one, and if I take this one, here we are having anti-clockwise rotation. Being it is a anti-clockwise, I am putting a minus m plus dm, one more moment, it should be equal to 0. Now simplify this expression, m plus f dx minus omega dx square divided by 2 minus m minus dm equal to 0. M is getting cancelled. Yes, when we are doing the mathematical analysis, small quantities with a higher order, we can keep them as 0. Then what is our observation, my dear friend? F dx equal to dm. What is dm? Dm, that is a change in bending moment between any two sections. Now if I bring this dx this side, dm divided by dx, it should be equal to F. So from moment equilibrium equations, we are having the relation between shear force as well as a bending moment. Now, when you are observing the left side part, now look at here, dm it is giving the change in bending moment between any two sections. If I take the change per unit length, this term we may call it as rate of change of bending moment. The rate of change of bending moment, mathematically it should be equal to shear force. As we know, when we are plotting the bending moment values, along the x direction we are placing the length of the beam, along y direction we are placing the bending moment values. Obviously we know that. So by observing this term dm divided by dx is also called slope of bending moment diagram. Slope of bending moment diagram. Slope of bending moment diagram, at one particular point it is giving the shear force acting at that point. So by observing the previous relation, we are having the relation between shear force and the rate of loading, and by taking the second equilibrium equation, we are getting the relation between rate of change of bending moment as well as shear force. That is the relations we are having. But these relations, observe this one, these relations are valid only for the distributed loads, not for the distributed moments or not for the moments. The distributed load is continuously acting over the beam. Maybe it may be uniformly distributed load, it may be uniformly varying load, or it may be sinusoidal loading condition, whatever it may be. These relations were derived for that continuous distributed loads only, my dear friends. Now, up to whatever the discussion we are having, so we are taking the numerical part related to that particular discussion. Where let's try to solve these 2-3 questions related to our discussion area. See the question, first question. What is our data? What is the data provided? The relation F equal to dm divided by dx. Relation F equal to dm divided by dx, where F and m are the shear force and bending moment respectively. This relation is not valid for which condition? 4 options are given. Out of 4 options, for which option this relation is not valid? Just now we are deriving the relation between bending moment as well as shear force. See the option. Option A, a simply supported beam subjected to the uniformly distributed load throughout the span of the beam. Option B, a simply supported beam subjected to the uniformly varying load throughout the span of the beam. Option C, a simply supported beam subjected to uniformly distributed moment throughout its span. And option D, none of the above. So when we are deriving these relations, one thing what we observed is, yes, these relations are valid for a beam subjected to the UDL as well as UVL. As I told you, that relations particularly we are derived for continuously distributed loading conditions. Maybe it is a uniformly distributed load, maybe it is a uniformly varying load, or maybe it is a sinusoidal loading condition, whatever it may be. That relation is particularly derived, for that continuously distributed loading condition. But when we are looking at the option C, see the option C, a simply supported beam subjected to the uniformly distributed load throughout its span. When I try to impose this relation for this condition, for option C, whether it is valid or not, I try to verify it. So let us take the option C. When I am taking the option C, let us consider a simply supported beam. We are having a simply supported beam, something like this, my dear friend. Let us take a simply supported beam. Let me mark the beam as AB. Here I am using uniformly distributed moment. Option C, it is given as uniformly distributed moment. Yes, we are using uniformly distributed moment. This is the length of the beam. Now, per unit length, the moment acting on the beam, just you can take it as a m Newton meter per meter. M Newton meter per meter. Over a unit length of the beam, the moment acting should be m Newton meter per meter. Now, what is our observation? For this load, whether this relation is valid or not. Now, you try to observe this one. I try to observe this one. Let us take this one. For this condition, first you try to find out the bending moment as well as the shear force at any one particular section. To find out the shear force and bending moment, first we require the support reactions. Now try to find out the support reactions. Now first my target is finding the support reactions. To find out the support reactions, first you can convert the uniformly distributed moment into the equivalent moment. Now how should I find out? What is the total moment acting on the beam? Total moment over a length of the beam, just it is nothing but m. Per unit length, moment is m, total length is L. M you can multiply with L. This is the total moment we are observing on this beam. It is acting at the centroid of a UDL spreading length. Let me say here somewhere it is acting, just imagine, with a magnitude of ml. Fine. Now how to find out the reaction at A and the reaction at B? When we are having the only moments acting on the beam, to find out the support reactions, maybe it is RA or RB, we are applying a shorter cut method. What is that? Net applied moment divided by span of the beam, it is giving the magnitude of the reactions. What is the net moment we are observing on the beam? ML is the net moment, and span it is L. L is getting cancelled, M. Now RA magnitude is M, RB magnitude is M. Then coming down to the direction for this one. Now, as we know, reactions are always opposite to the applied loads. Here applied moment we are having clockwise rotation. Then the reactions must be in anti-clockwise. So at A it is giving the downward direction. RA it is acting in downward direction. It is giving anti-clockwise rotation. And at B the reaction must be act in upward direction. This is the direction for both reactions. RA, it should be equal to M. RB, it is acting vertically upward direction with a magnitude of M. That is the case we are having. That is the case we are having. Reactions we are finding RA as well as this one. Then come down to the original diagram. Once we find out the reactions, then you come back to the original loading condition. Now, this is the original load acting on the beam. Here we are having reaction RA with a magnitude of M. Now we are using uniformly distributed moment over a length of L, M Newton meter per meter. Let us say this is A and this is B, or B equal to M we are having. Fine. Now to verify that relation, let us consider the section anywhere on the beam. Just I am considering the section at here, my dear friends. Now I try to write down the shear force relation as well as bending moment relation at this section by considering left hand side part. When we are calculating the shear force as well as the bending moment, what is the sign convention we are giving for the shear force and bending moment? Just now we have discussed. Apply that sign convention for analyzing the shear force as well as bending moment. Now my requirement is, first of all, what is the shear force acting at this section? Shear force acting at the section XX. Algebraic sum of the transverse forces, either left hand side of my section or right hand side of my section, it is giving the shear acting at that section. When I am considering left hand side, how many forces we are observing, my dear friend? Only one. When we are doing the analysis for the shear force, we should not consider this concentrated movement. Simply we are ignoring the effect of concentrated movements. Now let us take this one. If I take this one, only one force it is acting, RA, it is acting in downward direction. As per our sign convention, this is minus M, that is the shear force acting at our section. Then what about the bending moment? When I am talking about the bending moment at this section, now consider the bending moment. Now here, this section we are taking at a distance of x units from support A. This RA, it is giving the rotation in anti-clockwise direction. Write down that. Anti-clockwise direction, it is giving a negative sign, minus RA at a distance of x. Over a length of L, now look at here, rate of movement is M, but our requirement is over a length of this part. This part only we required. This part, my dear friend. Try to observe the applied moment over this one. When I am convert this one, M into X. M into X is that one. So, plus it is taking clockwise rotation plus Mx. This is the bending moment available at our selected section. What is RA value? What is RA value, my dear friend? RA value is M minus Mx plus Mx. Now, it should be equal to 0. In this particular case, shear force is available, but a bending moment is 0. Bending moment is 0. Now, you try to apply that relation. When I try to apply that relation, now look at here, dm divided by dx. That is relation it is given is equal to F. F equal to dm divided by dx. That is the relation it is given. As in this particular case, if you are observing, as in this particular case, being bending moment is 0, then here shear force also need to be 0. But does it is happened in this case? No. Now look at here. In this case, bending moment is 0, but shear force is available. But as for that relation, suppose, so when we are following that relation, so exactly this is not valid. This relation is not valid. This relation is not valid in the case of distributed moments, uniformly distributed moment. As per that relation, when I am considering the relation, as per relation, F equal to dm divided by dx. Suppose if shear force, what is the shear force available at the section? Minus M. If shear force is minus M, then corresponding bending moment must be minus Mx plus C. But that is not happened. In this case, bending moment is 0. That's why out of the given options, you try to observe this one. So, this relation is not valid when a beam is subjected to the uniformly distributed moment. So, that relation is particularly derived only for the continuously distributed loads, not for the moments. Maybe it is a uniformly distributed load, maybe it is a uniformly varying load, or maybe it is a sinusoidal loading condition. But this relation is not valid for distributed moments. That is our observation from this question. So, this question is related to the relation between shear force and bending moment. Now, let's move on to the another question. Now, see another interesting question. Read the question carefully. It is related to the bending moment calculation. How should we find out the bending moment at one particular point? Two people weighing with a magnitude of W, each one are sitting on a plank of length L, floating on water. Initially, we are having a plank, it is floating on water, and two people are sitting at a distance of L by 4 from each end. Considering the specific weight of the plank, this is very important. That means here specific weight of the plank is given. That means we need to account the self weight also. In addition to the weight of these two persons, we need to account the self weight of the plank also. when we are finding the bending moment at the center of the plank. What is the bending moment available at the center of the plank? Whether it is 0 or sagging or hogging or none of this. First of all, let me observe this one. Here the plank is floating on water, first observation. Let me take here two important aspects we need to consider. One, water pressure we need to take into the consideration because it is floating on water. Second one, being specific weight is given, we need to account the self-weight of the plank in addition to the two persons' weight. Then we are calculating the bending moment. If you notice these points, then we can easily solve this question. Now look at here. Suppose this is the plank we are having. Let us take the length of the plank. If you take, it is L units. I am taking this plank. On this plank, at a distance of L by 4 from each end, two people are sitting. That weight of each people, it is a W. Let us take this is a L divided by 4. It is also L divided by 4. Fine. And being it is floating on water, let us take the water pressure. So this is the water we are having. When you consider the effect of buoyancy force, water pressure, it will be act uniformly distributed manner over the plank. This is the water we are having. This is the water we are having. Water pressure, it is acting in upward direction. Now, let us take this one. So, water pressure, it is acting something like this, my dear friends. So, we need to account the effect of buoyancy force, as we know that. This is. Let us take the rate of load. You can consider this is a Q per unit length. Maybe it is kilonewton per meter or newton per meter, whatever it may be. Intensity of load. As one more condition is given. What is that condition? Being we need to account the self-weight. Self-weight of the plank is given. Self-weight, it will be act as a uniformly distributed load. Self-weight, it is acting vertically downward direction in the manner of UDL. This is. Yes, so this is complete diagram of the given data. The rate of loading for this one, you can consider it is a P per unit length. What we require? We need to find out the bending moment. Nature, here it is a indirectly nature we need to identify. Let us at the center. This is. Take the section at the center. Now at center, this is the distance we are having. This is the distance we are having, my dear friend. This is L by 2 we are having. Fine. We need to find out the bending moment at the mid-span of the beam. First of all, try to find out the relation between WP and Q. Should I consider the force equilibrium condition? Why not? So when I am taking the force equilibrium condition, summation of forces along y direction equal to 0. Upward force I may consider as positive, downward force I may consider as negative. Upward forces I am writing one side, downward forces I am writing another side, my dear friend. Here, look at here, Q into L. And here we are having P into L, 2W, W plus W, 2W plus P into L. One side I am taking 2W plus P into L. I am taking one side, my dear friend. It should be equal to Q into L. Bring this term this side. If I take this one, clearly I can write 2W equal to Q minus P into L. W equal to how much we are having? W equal to Q minus P into L divided by 2. This is the W value we are having. This is the W value we are having, right? Fine. This is W value. We know the W value. Now, let us take the section at midpoint and consider the left hand side forces. to write down the bending equation at the section. You just try to write down the bending equation by considering left hand side forces of my section. Bending moment at the section equal to how many forces we are having. First, let you take this one. It is L by 4. Then it is also L by 4, being it is a center point. So how it is acting? Downward direction. So first I am taking the effect of that one, minus W at a distance of L by 4, fine. Then take the path of downward UDL up to this one, my dear friend, up to this one. So UDL it is taking downward direction. Now minus P into L by 2 into L by 4 distance of this load. Now one more load is there. What is that load? This load we are having. This load, upward UDL. What is the magnitude of this one? Q. Being it is upward, it is positive, plus Q into L by 2 is the load. Distance of this load is L by 4. This is the bending moment available at the mid-span of the given plank. Now, just to simplify this one, minus W into L by 4 plus Q minus minus P, this is P, divided by 2 is there. Is it right or not? Into L here we are having. Fine. Then the distance of this one, if I take this one, L by 4. That's it. We are having. What is Q minus P divided by 2 into L? Q minus P into L divided by 2, it is nothing but W. So this term, it should be equal to W. This term, when I am observing this term, it should be equal to W. So when you read at this one, bending moment at midpoint, x equal to L by 2 equal to minus W L divided by 4 plus W L divided by 4. It should be equal to 0. This is the way how you are finding the bending moment at a given section. Either you should consider left hand side forces or you should consider right hand side forces. What is the option we are having in this case? Yes, this is the correct answer, 0. The bending moment available in this particular case is 0 we are having, right? Now, let's move on to another interesting question. Now, try to read the question. Again, to solve this question, again we require the relation between rate of loading, shear force and bending moment. Now, try to read the question. What is the data given in the problem? For a particular loading on the beam, the shear force diagram is shown in the figure. Yes, so this is a shear force diagram. The given diagram, it is a shear force diagram. What we require? There is no external moment acting on the beam. Another information, no moments are acting on the beam. Completely all are transfer loads. Then the magnitude of rate of loading in terms of kilonewton per meter on the beam for the portion BC. In part of BC, how much rate of loading it is acting? That is first asking. What is the rate of loading in the portion BC? This is our requirement. And the slope of bending moment diagram for the portion AB. For portion AB, slope of bending moment diagram, dm divided by dx. It is for AB part. It is nothing but it is giving the slope of bending moment diagram. Slope of bending moment diagram at a particular section should be equal to shear force acting in that particular section, as we know that. These two we required, my dear friends. Now let us take this one first. Now what is the relation between shear force and rate of loading? Just you can think it. Now already we are deriving the relations for shear force and rate of loading. From that relation, let us try to apply that relation. dF divided by dx, it should be equal to minus omega. Minus, it is indicating only direction of loading, my dear friend, as per our relations. Right? This is rate of loading. Minus indicating your loading is in downward direction. Now, if you are observing the denominator, it is giving the change in shear force between any two sections. And this is giving the length of that, or the distance between the two sections, denominator part. Right? Now, let's try to observe this one. Now, if I apply that relation for a portion BC, because we require the rate of loading in part BC, this is we are having. This part you can consider. This part, my dear friends. This part. Now, what is the shear force available at here? 8 units. What is the shear force available at C? 0 units we are having. 0 units. Shear force at C minus shear force at B. Just I am using that relation. This relation I am rewriting as per our requirement. Shear available at point C minus a shear available at point B divided by length of BC segment. It should be equal to rate of loading acting in the BC segment. Shear available at C 0, just we are verified, and shear available at B, it is 8 units. Length of BC, just you can observe. Length of BC, if you are taking, it is 2 meters. Now, this is 2 meters, it should be equal to omega. So, omega equal to how much, my dear friend? 4 kilonewton per meter. So, omega in BC segment, if you are observing, 4. So, just to identify the relations first. So, here there is no 4, eliminate this one. Here there is no 4, eliminate these options. Now, either option B or option D is correct. Now, to get the correct option, then what we require next one? This condition, my dear friend. dm divided by dx, slope of bending moment diagram. What is the relation between slope of bending moment diagram to the shear force? Now, look at here. Slope of bending moment diagram at a point, it is giving the shear force acting. Now, this is the shear force available. This is the shear available. This is the shear available in AB segment. So, what is the shear available in AB segment? That is minus 2. Minus 2. Therefore, dm divided by dx in segment AB, it should be equal to minus 2. dm divided by dx, it is nothing but slope of BMD. Slope of BMD. Slope of BMD. Slope of BMD, it should be equal to minus 2. So, which one is correct, my dear friends? Option B is correct, my dear friends. Right? This is another problem we are solving by applying the relation between a rate of loading condition as well as a shear force and a bending moment. Now, another interesting thing. Now, just you can observe this. Now, this is not 2. This is L square. Some printing error we are having. Let us take another interesting problem. Try solve this problem. For the beam shown in the figure, the magnitude of maximum bending moment is k omega L square divided by 3. It is NAT type questions. Previously we are observing MCQ. Now we are taking NAT question. Right? So the maximum bending moment value, how much it is given for the loaded beam? K omega L square divided by 3, my dear friends. Then what we required? What is the K value we are having? What is the K value we are having in this particular problem? What is the K value we are having? Let us try this one. This is a simply supported beam, and let us mark this as A, let us mark this as a B, and let us mark this as C. Now, look at here. If you take this one, load, it is symmetrically placed over the beam. To get the support reactions, I am using a symmetry principle. Now, what is the total load acting on the beam? Just you try to observe total load acting on the beam. Total load on beam. Total load on beam. Area of triangle, it is giving the total load on beam. It should be equal to half into omega into total length of the beam 2L 2 is getting cancelled, it is omega L. That is omega L. That omega L, it is exactly passing through the centroid of this triangle. This is, here it is taking, my dear friend. This is omega L we are having, omega L, fine. Right? Now, let's try to find out RA and RB. To get the RA or RB, I am using a symmetry principle. When I am applying the symmetry principle, due to symmetry, RA should be equal to RB. Generally, to find out the support reactions, we are using the equations of equilibrium, but sometimes, most of the times, without using the equilibrium equations, we try to get the support reactions. Something like this. If the load is symmetrical load, directly I am applying the symmetry. If only concentrated moments are acting, in that condition also we are using the short Rekha, that is net moment divided by length of the beam. Right? Now, due to symmetry, RA or RB equal to total load divided by 2. What is total load? Omega L divided by 2. So, here it is omega L divided by 2. And one important thing we know, when the load is symmetrically placed on a simply supported beam, zero shear force or maximum bending moment is available at the midspan of the beam. So, by knowing that point, I directly try to find out the bending moment at point C. That is, when I am taking this into the consideration, let us take this one. So, due to the symmetry, as we know that, due to symmetry at midspan, bending moment is maximum. So, you try to find out the bending moment at a point C. Now, just I reproduce the beam. This is the beam we are having. Let us take this one here. RA is available. What is the magnitude of RA? Omega L divided by 2. So, somewhere here you can consider point C, midpoint. What is the distance between A and C? L units. And try to observe the distributed load in the portion BAC. This is the distributed load we are having. This is the distributed load. What is the rate of loading is given? Omega. Right? First of all, before writing the bending equation, you should convert this into equivalent load. When I am converting this triangular load into equivalent load, it is exactly passing through the centroid of the given triangle. This is centroid point. Now, half omega and L, that is the load, equivalent load for this triangle. Now, what is the distance between C and this load? Because we need to, yes, we require the bending moment at point C. Now, when you take this one, the distance between load and point C, it is L by 3. Fine. Now, write down the bending equation at point C. Bending moment will be maximum at C. Oh, consider this one. Just I am considering this side forces. Let me take the section at here. This is the section we are having. I am considering left hand side forces, my dear friend. How many forces we are having? One, it is RA. Second one is this downward load. RA, it is giving sagging effect at a distance of L units. So, first you can take that effect, RA at a distance of L units minus. Why it is minus? It is giving anti-clockwise rotation about C. Omega L divided by 2 at a distance of L by 3, my dear friends. Now, simplify this one. RA value how much? RA value omega L divided by 2 into L. And here if I take this one, omega L divided by 2 into L by 3 we are having. Is it right or not? You can take omega L divided by 2, you can take it as common. Then it is L minus L by 3. 3 minus 1, 2, 2. 2 na? Just simplify this one. 2 omega L square divided by 6. It should be equal to omega L square divided by 6. Sorry, 3. omega L square divided by 3 we are having. Just 3 we are having. But what is the bending moment available at C? It is given as M max equal to, given that M max equal to, it is nothing but I can write it as 1. M max equal to 1 into omega L square divided by 2. Compare that to 2. When I compare that to, it is given as K. Finally, what is K value we are having? K equal to 1. That is the way how we are analyzing the problems from the concept of shear force and bending moment diagrams. Hope you understand. All the best for your preparation, my dear friends. See you.